Okay, everyone, please take your seats. Okay, we are going to begin our first panel for the conference today. I have the distinct pleasure to introduce Adriana Mitchell. She will be moderating the panel titled Pixels to Planets, the AI Imaging Frontier. Adriana is a PhD student candidate in the MIT Aeroastro department. She is affiliated with the Astrodynamics Robotics Control, or Space Robotics and Control Lab, and Dr. Richard Linares is her advisor. She does research and is a research affiliate at NASA JPL, working to improve optical navigation during entry, descent, and landing on other planetary bodies. And her research interests include deep space optical navigation, satellite-based localization, and remote sensing. And I will let her to introduce our panel. Take it from here, Adriana.
Thanks, Mark, for the introduction. I'm so excited to present this panel to everyone today. We have some really exciting experts lined up to discuss not only AI and space imaging, but also their expertise in controls and other areas. I created this panel specifically because AI has had such a revolutionary impact in computer vision and image processing, and we can see that it's an area where AI has been able to outperform humans on image classifications and detection tasks. But there's a lot of interesting challenges when you get to applying AI to space, and I'm excited to hear the discussions on that. So I'm going to go ahead and introduce the panelists. We have a really great lineup. So we have Professor Roberto Furfaro, who is a professor of systems and industrial engineering, and also the director of the Space Situational Awareness at University of Arizona. We have Dr. Mikhail Klassen, a senior machine learning engineer at Planet. We also have Professor Victor Rodriguez-Fernandez, associate professor in computer science at the Technical University of Madrid. And we also have Dr. Rebecca Russell, perception and embedded machine learning group at Draper. So I would love if each of the panelists could just take a few minutes to introduce themselves and their key research areas, and then I'll go ahead and get started with our first questions.
All right. Thank you very much for the invitation. It's a pleasure to be here, especially considering we have a long-standing collaboration with Professor Linares here at MIT. And yes, as I said, as a professor, systems engineering, also aerospace and mechanical engineering, have a dual affiliation. My research and the lab, my space systems engineering lab, lives kind of at the intersection between AI and spaceflight mechanics in general, right? I would say we develop methods for guidance, control, and navigation, driven by, for example, reinforcement learning, kind of approach for planetary landing, close proximity operations. We also have project with the Space Forces and about tracking objects using telescopes, right, and images, and using also AI methods to develop, for example, orbit determination, things like that in the cislunar space, which is the new frontier in that regard. The last, I'm also the target follow-up working group lead for the NASA Neo Surveyor mission we're going to launch in 2027. Maybe we'll talk a little bit about this because there is an AI component there. Okay. Thank you.
Thanks, Adriana. My name is Mikhail Klassen, senior machine learning engineer at Planet Labs. At Planet, I work in the applied machine learning group. So we apply deep learning models, computer vision models, to remote sensing data from Planet's approximately 200 satellites that orbit the Earth continuously. Planet monitors all of the Earth's landmass, monitoring it, taking pictures of all of Earth's landmass every single day. And so that results in huge volumes of imagery, and it's our team's work to do analytics on top of that, and it's a great pleasure to work on that.
Thank you, Adriana. My name is Victor Rodriguez-Fernandez, and I am an associate professor in Universidad Politécnica de Madrid. And I used to collaborate with Richard Linares and his group last year, and I'm still collaborating with him in many projects related to the application of AI to space. And that's basically what I'm doing now research-wise. Personally, I'm AI fanatic too, so I like everything related to AI, and I like keeping up with the literature and the news in many, many ways to see what potential there is in the new developments for different applications, but especially space. And yeah, excited to be here. Thank you.
And I'm Rebecca Russell. I'm a principal machine learning scientist at Draper. I work primarily on deep learning for applications in autonomy, guidance, navigation, and control. Most of my interests right now are in how we can really interface deep learning safely with our expert algorithms, so doing uncertainty quantification and other ways to make it work with existing systems and make these systems more trustworthy and robust instead of scary machine learning infused nightmare machines.
Thank you so much for those introductions. I'm going to go ahead and get started with our first question, which I think probably a lot of people, when they think about AI, they think, is it this new fad? I'm seeing it being applied everywhere. Of course, in different technical aspects, we've seen really great use cases. So I was wondering, what are these problems that we want to solve in space that is difficult for humans to do, that AIs would enable this additional autonomy or enable this new exploration? What is it about applying AI that is so important that you've seen make an impact? And I'd love to just go down the line. And if there's a project you'd like to highlight, anything like that.
All right, I guess I'll start.
Go ahead.
Just order. All right, so personally, I have a long standing interest in AI, and I worked in space exploration quite a bit for a while. For example, I was the system lead for the OSIRIS-REx asteroid sample return mission that, we just a couple of years ago returned the sample, back. And so I went through the development of the life cycle of the mission, and I there identify a lot of opportunities where AI could play a role. However, NASA tends to be, unfortunately, more, and Steve earlier pointed out, very conservative, right? Because those technologies are considered somehow higher risk, although I believe that as we move forward, things, this constraint is going to be relaxed. And one of the things that, for example, consider the space exploration generally of the solar system, you have major issues where that AI can solve. One of the problems, for example, let's say that we want to go, and we're going to go with the Dragonfly to Titan, right? It's an exciting place in the solar system, and the light time communication is basically 90 minutes one way. What it means that basically just to send a signal and receive back, you're talking about 3 hours, okay? Now, if an helicopter's like Dragonflies, right, flying around, find something interesting from a scientific point of view, there is no way you can react immediately just with a command from the ground, okay? So AI should play a role. Now, a long time ago, I started kind of a campaign with my fellow colleagues, planetary scientists, right? I come from engineering, try to convince them that, for example, we should use AI, to mimic the reasoning and capture a little bit the reasoning that scientists do, because there's no way, that they can, take data, something that happens serendipitous and where the system has to react. And indeed, at the time, I started working, and it was way before the wave of deep learning, where things now are much better, in that regard. I started developing, for example, something called the cognitive maps or fuzzy cognitive maps in that specific, where I was trying to capture their expert reasoning. Actually, as a matter of fact, this approach is also being used now in the new mission, the Neo Surveyor, where we're going to launch in 2027. Neo Surveyor is a NASA mission led by us at the University of Arizona and built by Jet Propulsion Laboratory and Ball Aerospace and a few others there. So what we're doing, we're going up to the L1 point, the Lagrange point between the Earth and Sun, and try to map according to what is called the 2005 George Brown Act, which is a Congress act, map greater than 90% of all asteroids bigger than 140 meters, right? Because those are the hazardous one that we don't know. We know everything above 1 kilometer size, but there is a huge gap there, right? Problem is that the spacecraft is going to do a survey, is going to detect, according to the population model, a lot of data, and there's no way that all the data can be looked one-on-one. I'm talking about in the first few months, you're talking about somewhere between 1,000, 10,000 a day. So we're developing an expert-based decision systems based on Bayesian network cognitive maps that capture, where we are capturing basically the knowledge that planetary scientists, reason when they reason over the data. Okay, to be honest, I'd rather do a data-driven kind of approach, right? But whenever you talk with scientists, and I experienced, talking with some people in other domains, but a couple of weeks ago, doctors act the same things. They got threatened by AI systems. And I remember the first reaction when I was talking to planetary scientists and showing, reasoning over Titan, for example, cryovolcanism, that the system can do it, right, and reach the same conclusion as you do. The reaction was like, are you trying to get me out of a job? And apparently, doctors are doing the same. When they show some of these machines, results that can do better and something else, it's like, what are you trying to do here? So, anyway, I don't want to take a lot more time, but AI, for example, in terms of space exploration, can play a huge role in terms of really exploring the unknown. And either you do data-driven or you do with the AI that is knowledge-based. That's a huge contribution needs to happen. Sorry.
Sure. So I'll talk maybe a little bit about how we capture imagery right now over the planet and how we did this historically. Some of the earliest remote sensing work, was still shot on film cameras in space. So you had these spy satellites that had been launched with film cameras shooting film in these canisters, which would then get deployed down in a pod that would fall to the Earth, deploy a parachute over the ocean, and then a military plane would scoop this thing out of the sky. And if the plane failed, then at least you knew it was going to hit the ocean and sink to the bottom of the ocean, and that secret footage would be lost or destroyed. And it's wild to me that this was how things were done historically. And now, of course, we have digital cameras in space. And at Planet Labs, we pioneered agile aerospace. So the thinking was, well, you replace your smartphone every 3 years with the latest technology. Why aren't we doing this with satellites? So there's a fleet of about 200 of these small sats, mostly, that get replaced every few years, and Planet is taking like 30 terabytes of data downlinked every single day, and no human analyst could actually go through that much data. In the past, obviously, you'd have human analysts reviewing little, the photographic footage, and now we have 30 terabytes of GeoTIFF files, and what do you do with that? It's the role of AI to be able to get useful insight from that data. And one of the example projects that I can talk about is our rodent building detection model. So much like one of the lightning talks we heard earlier today, we use image segmentation models to look at a picture and classify every pixel as either a road, a building, or neither. And where this is being used to great effect is over the Brazilian Amazon. So Planet has a contract with the government of Brazil where we image the entire Amazon rainforest, and we detect any new roads that are being built. And oftentimes this allows the Brazilian federal police to then do enforcement where illegal roads are being put in, which are usually the harbingers of illegal mining activity or illegal deforestation. And because of this program, the government of Brazil has actually been able to recover about $2 billion worth just in terms of fines or seized assets And that is something that Planet helped to facilitate, and that's something that our machine learning models help facilitate. And so that's a really exciting use case, and some of the good that AI is doing in the world using remote sensing. So I'll just leave it at that for now.
Thanks.
Oh, okay. So I think that AI enabled back in the day when this deep learning revolution exploded, it's like we started revisiting some problems that we didn't consider before, like dealing with in a data-driven way, because everything was like implemented based on expert system, which every rule of the system. And these last 10 years since 2012, that has been we had this single weapon like data, neural networks, and GPUs. And so all of us basically got our past problems that we were interested in, like control, like image classification, like tracking, navigation, and try to turn into this new paradigm. And I think now it's happening the same. And we are living the same thing now with language. So I think it's time now to revisit again some of the problems that we left in the past and revisit them again with language models and what this new paradigm brings. And we might have new surprises. Together with the ARCLab, we put yesterday in arXiv one paper about what about using language models to interface, basically to do the control of one spacecraft, which sounds crazy, and it's crazy. But it turns out that if you rely on the base knowledge that a language model has of things like Astrodynamics, because it has been fed with all the books that you can imagine, you can fine-tune them to work as a kind of a surrogate of a reinforcement learning algorithm, needing much less data than you would need to train from scratch something like RL that needs to learn physics, needs to learn orbital dynamics, and so on. I'm really excited about this because I think in the same way that deep learning opened a new era of revisiting problems in a data-driven way, everyone buying GPUs, I think now it's time to revisit again some of the problems with this LLM or pre-trained transfer learning perspective.
Yeah, so I mostly work in the autonomy space, and machine learning's obviously been a huge enabling technology for autonomous systems on Earth. But space is kind of a different story. When we're talking about autonomous space vehicles, we have a much higher bar for being able to deploy machine learning algorithms. We're usually really computationally constrained. We can't just slap a bunch of GPUs on our vehicle. We often don't have much data. We have to rely on simulated data a lot. And in general, if the machine learning algorithm makes a mistake, it can potentially cause a complete mission failure. You have one chance to get it right with the real data. So it's really challenging compared to domains on the Earth. One application that we're looking at Draper, where we do computer vision right now, where machine learning can potentially make a big difference, is terrain relative navigation, which is something we're using in our lunar lander that is part of the NASA CLIPS program. So that's Commercial Lunar Payload Services. So terrain relative navigation essentially allows the system to figure out where it is based on some reference satellite imagery. Typically, it uses template matching with small patches of imagery to look in the camera view from the lander and figure out where, find correspondences. It passes that into the navigation system. That's really in the control loop for the vehicle. And for Earth-based applications of terrain relative navigation on a plane or on some landing system on the Earth, we found that machine learning can do this a lot better than just a simple template matching algorithm because it's more robust to minor differences in the lighting or shadows or dust, other more superficial characteristics that don't change the underlying content of the image. But just making the system a little more accurate isn't enough in space compared to on the Earth, because it's hard to trust when it was maybe trained on simulated data. We have really limited high-resolution data of the moon under the lighting conditions that we need. So one thing that we're looking at right now, which we've proven out on Earth-based applications, is uncertainty quantification with machine learning. So one thing you can't do easily in existing terrain relative navigation systems is for a given match, say how confident you are in that match. You have to rely on a lot of redundancies in the matches. You have to rely on your navigation filter to figure out what measurements are trustworthy. But machine learning, we found, is better able to predict, is this a good match? Is this something that we can trust? What kind of covariance do we have on this measurement? And then that's also a much more lightweight application of machine learning. It plays much nicer with an existing, more proven algorithm that doesn't use machine learning. So that's one place where we're hoping to use machine learning potentially as part of a space autonomous system in the next few years.
Thank you. Those are all great.
Yeah, I want to follow up on some, because we touched some interesting, topics, and I want to give you a little bit of perspective so we start opening a little bit of discussion in this regard. Touched a couple of things, the use of advanced, I would say, large language model for guidance, control, and navigation, and you touch also on the problem of the different chain, for example, the navigation part, done with machine learning. Now, interestingly enough, I think that this is, I completely, of course, agree with you in terms of the interesting direction that, that we can take in terms of using something like ChatGPT for control. But there is a general problem that society, from a perspective of perception, we need to solve, okay? Let me give you an example. This is, of course, not space, but I got from DoD a contract about hypersonic systems, right? In using AI, more specifically Meta-RL, for hypersonic systems, right? Why? Because hypersonic systems are really hard. Nobody knows exactly how the fluid dynamics works. It's highly nonlinear, so AI system can capture kind of this, right? Problem is that whenever we design systems and we beat the state of the art, of these kind of things, the first question that comes back is, what are the phase margin and the gain margin of your control systems, right? If you guys are familiar, phase margin and gain margin comes from linear control theory. Neural nets are inherently nonlinear. So my answer is well, there's no such a thing there, right? Yeah. The second thing is, how do you know what he's doing? Explainability. Okay, so the problem is that the space world, I would say aero/space world, lives in a certification, procedure that is uses certificates that are based on linear theory. Okay, so if we really want to push, the envelope of the next generation of this, we need to convince I would say I wouldn't say the aerospace research community, just the certification, I would say, community, right? That we need to find new metrics to certify this system, right? Everybody's talking about trustworthy, but how do you physically certify before flying these kind of systems?
How did Tesla do to put neural networks in a Tesla, in a self-driving car?
Well, in a self-driving car, well, it's the same problem, right?
Yeah, but you can find them right now, and
yeah, but they are not certified, right? I mean, they're not certified. They didn't go through the certification process, right? I was talking more about flight system where I'm.
Yeah, but
of course, the regulation that you do with cars is a little bit different, but still, you have systems like, if you go in Phoenix, Arizona, where I am, you have this self-driving car collecting data, but those are experimental, system. They're not certified, for the public to use it. That's part of the thing, right? As completely autonomous system.
Completely autonomous? No, absolutely
Talking about
not.
completely autonomous
no,
system.
Not completely.
When we
no.
fly system
Yeah,
completely
I see.
autonomous in aerospace or in space, if you want to land on the moon, you have the same issue. When you design a mission, if you want to put a new, brain or software that does GNC, you will go through the same level of certification, right? That will require gain margin and phase margin. The question is, how do you push it out? How do you basically convince this is not the right metrics that you want to certify the system? You need a new set of metrics to certify AI system, okay?
Absolutely.
The problem that you have is that the system has always what they call the infinite modes, right, of behavior, right? I remember there was a while ago, I was talking to the chief engineer for the I think it was at the time the F-15, one of the systems that were trying to, put some adaptive controllers, not even AI. And adaptive control, by definition, they cannot be certified through the standard approach where you have mode 1 of behavior, mode 2, mode 3, right? When you do the system engineering there, what you do, you test mode 1, you test mode 2, you test mode 3, and you're done. When you have an adaptive or even better, an AI system, how you certify something that has potentially infinite modes of behavior, right? So the answer of the chief engineer was like, no, we test. We tested, to exhaustion, of funding.
To the exhaustion of funding.
Exhaustion of funding, which means they were not, according to the standard way of doing things, they were not really able to really provide confidence that the system would work according to the standard program.
The standard way of doing things is a function of not being allowed to fail. If it's a multi-billion-dollar mission, you have one chance to get it right. Everything has to be tested to exhaustion. But I'm wondering about a future where, as payload costs come down exponentially, and Starship is going to open up whole new opportunities for science, for business and space. What happens when a student-led team here at MIT puts an autonomous rover on the moon because it was actually something they could do affordably? And you could slap whatever the most recent version of open source LLM as the controller in that rover, and we see how it performs.
In the same way that you have Waymo cars in San Francisco, and they are experiments, but they drive alone. So when it gets, I understand that if it's $1 billion mission, yeah.
Right. What if it's a $100,000 mission, and that's a grant that a student team wins?
It makes more sense to open this certification and to
loosen some of the constraints.
And it's,
I think, my point is that you've got to change the way you certify the system. The current way of doing business doesn't work for the AI system, and is hampering the ability to deploy, the system. And I can tell you that in the aerospace world is very marked because of this idea.
I understand. Yeah.
What happens is that NASA works on a paradigm which was okay for the human exploration. Failure is not an option. Okay, and we transferred this framework into robotics, where maybe you can fail. Yeah, it's a $1 billion mission, right? But it's all perception from the community, right? It's perception, because $1 billion for a country like the United States, it's literally a drop in the bucket, right? If you think this way. But for the common person, if you hear $1 billion mission, oh my God, we're dropping money left and right. So that's a different story. There is a risk posture. What I notice, however, that when things get more complicated, like now in the current, with the whole world politics evolving, right? When we are under threat, other entities like Department of Defense are more willing, I can tell, to take risks, right? Because the risk of not doing outweigh, the cost.
Yeah, and Roberto, I'd even go so far as to say, perhaps some of our industry partners could comment on that as well, since they're deploying AI on their technology. And I'd love to hear a little bit about the metrics you use and the uncertainty quantification you do to enable robust and reliable use of AI. If Rebecca and Mikhail, you'd like to talk on that.
So the V&V question is really complicated. Part of the reason why we can look at using machine learning on the Draper manned lunar landers because we have total control over what V&V is acceptable. So NASA isn't telling us what to do necessarily there. Still, obviously, there's like a lot of culture kind of embedded in people who work in space. I mostly do not work in space, so I work in all sorts of other domains. So maybe I'm bringing more risk there. Obviously, it's a different calculation when it's like a manned mission versus unmanned missions. And as they get cheaper and cheaper, like the CLIPS missions are like order $100 million, which is a lot of money, but it's cheap compared to how much it used to cost to go to the moon. So you start being able to accept higher and higher risk with that. And yeah, a lot of it does rely on like testing, Monte Carlo testing, whatever Earth-based testing you can do. There's only, you almost have to like give up on like certification and explainability only goes so far also when you're talking about like an autonomous system where there's no human in the loop in general. Explainability is different when you're talking about interfacing with a person who has to make a decision based on some machine learning predictions. But yeah, it just looks different when you have a person versus an autonomous system as part of this loop.
I wonder if the methods you've been using at Draper more on like the Earth-based application, like the metrics you've been using to assess AI, do you think those could be used in space? Or like what your opinion on that?
Well, yeah, so most of I guess the metrics in the end are like the system performance and the looking at different aspects of like reliability and robustness, trying to capture those, because it's one thing, usually in machine learning, you're just like improving accuracy, but that's usually not what you care about with an autonomous system. You want to improve like robustness and resilience. And so it's different metrics that capture that. So you're really looking at like those failure modes and probing those failure modes and trying to understand how realistic those are.
Yeah, thank you for that answer. And Mikhail, if you would like to comment on that.
I don't think I have anything to comment on that. That's more of a space systems question.
Yeah, so I think we've brought up a lot of interesting topics so far, thinking about how we need AI because we can't predict every scenario, but also is it hard to use AI because we can't test in every scenario? But also, can we augment science work with AI instead of, replacing scientists potentially on these exploratory missions? One question I'm really interested in also is that, there's a lot of machine learning papers that come out like almost every week. It's an interesting field. There's always new and exciting things happening. I had questions for both the academic side and also the industrial side. How do you stay on top of that? And how do you evaluate these papers for potential adoption or collaboration? And maybe we can start from the other side this time.
Yeah, I mean, the papers are coming out really quickly, but meaningful progress in terms of conceptual progress isn't changing that much. So it's always just better results with more data, little architecture tweaks. It's rare that there's big paradigm shifts in machine learning. So to some degree, you have to avoid being distracted by the most recent hype and focus on the fundamentals. A lot of times the algorithms that work are ancient by deep learning standards, 5+ years ago, and those work, especially when you're limited in how much data you have, those usually work as well as the latest and greatest algorithm when you have approximately infinite data.
One problem that I see is it's super hard. I mean, I literally have sometimes anxiety because I feel that I cannot follow the literature and the applications and the possibilities. And there's also a gap because if you follow the open science, you can see more or less incremental advances, conferences and so on. But then that's the research of big techs like Google and OpenAI. And you might be creating your application, integrating all of the new, let's say, LLM stuff, architectures, tricks, prompts. And then suddenly OpenAI releases something that makes your pipeline deprecated automatically because their model does it automatically in one shot. And it's then, so you have this incremental progress of the open AI, I was going to say, of real open AI, and you have this like not so incremental like booms that happens with when OpenAI releases something like Sora for video or GPT-4, which like makes everyone like shakes like, oh, what's happening with this project that I had right now? Maybe this new model can solve it without any of the things that I did keeping up the literature of the last year. So it's like that combination, which it's quite hard.
So what I'm waiting for is an LLM that is reading the archive continuously and just giving me summaries of the latest research.
There's one. This guy from OpenAI, Andrei Karpathy, did one tool that it's called Archive Sanity. That it basically creates your archive preferences so that you have only like your recommendations. It's like the Amazon recommendations for your archive daily mailing list. I don't know how it works because I don't use it often, but there are things.
Well, yeah. So I mean, on a more serious note, LLMs are actually helping me keep up with the field. I might take a paper, a PDF, upload it to ChatGPT, and then begin engaging with that paper. And if, let's say, there's an introduction of a new architectural element in a neural network, or they're using a particular neural network that I'm not familiar with, I might ask questions about that. And ChatGPT is usually quite good at giving me like the history of that type of architecture. What were the seminal papers? When was it introduced? What were the changes made over time? What are the caveats, the pros and cons of using this type of network? And of course, then like you don't treat all of that as true necessarily. You take it with a grain of salt. You go and you look stuff up, but it helps provide context. And then in terms of other ways of just keeping up, like it's you have to be plugged into a community. I count on my colleagues at work, and we share papers with each other. We are on Slack channels where if an interesting paper comes up that we think might be relevant for AI and remote sensing, we share that with others. We discuss them, and yes, to Rebecca's point, a lot of work is sort of incremental. We got some better data. We tweaked this model, and you can sort of treat those as like these incremental bits of progress, but every so often there is a paradigm shift, like when the Transformer paper dropped in 2017, that changed the course of AI research. But maybe that was only realized after the fact. So we try to keep on top of what's happening there, but it's impossible.
And Twitter is important too.
Twitter is surprisingly important.
Yeah.
I convinced myself that honestly, from an academic perspective, workforce development, we need the new generation of people. What I notice is the following, and now things are changing with LLM, right? But there's a lot of going on in the computer science community. The problem is that if you take some scientists working specifically on just more general type of AI and try to have them tackle a guidance problem, for example, landing on the moon, it's just simply, no matter what is the best technique that could work, right? It's just not going to happen. They're not going to be able to work on this. On the other side, if you take GNC engineers, they're not going to be able to even understand closely unless they have a humongous effort. And I personally, I'm struggling with that because I'm on the intersect. My training is on the standard aerospace GNC control. It happens that 20 years ago I didn't know it was winter AI, but I was a student. What did I know, right? And I just loved neural networks, so I started this trend, right? Now so I kind of developed both, but I'm struggling because keeping up with what's happening, right, is always hard. But what I notice more and more is that interacting with more classically trained GNC engineers, they just don't have an understanding of the depth of the revolution that is happening.
Yeah.
So the question is, how do you create a new generation of students, I would say, that is able to handle both effectively. Doesn't mean, in terms of amount of information they can handle, but they have an understanding of both so they can merge the two things, okay? And I think this is a critical aspect also to transfer, because there's a lot of good stuff that is happening, for example, in reinforcement learning, in meta learning, in LLM. But if you don't understand the control problem, right? Or if you don't understand how classical is done and how can you embed, right? You're not gonna, the best technique that can potentially be used is not gonna be transferred.
Yeah.
It's just as simple, okay? Unless you have a new generation of people that are sensitive and understand what's happening on the other side and find the key to transfer this on the other.
It's natural. I think future generations will have it. Like
Right.
whoever undergrad now doing space engineering that is using ChatGPT to learn, I don't think it can have the same resistance to AI than the old generations.
It's not just a matter of only resistance, it's just a matter to understand the domain. You need domain experts that understand computer science and understand AI. And I feel like we're still lacking of those, right? Because the way we train them, and I've seen it, right? Just classical school that train them in, spaceflight mechanics, astrodynamics. Yeah, they have students that take 1 or 2 classes in AI or machine learning because they're interested. But they don't have that, and I don't have an answer, a solution to that. But I can tell they don't have that, what you really need to evaluate techniques that are coming now out of, OpenAI and transfer to a control problem, right?
Yeah, yeah.
I mean, with the LLM idea that you had, we're just starting, right? We're just starting there, and but it will take a lot of effort to understand.
It'll be a new and emerging discipline.
Discipline, yeah, that's right.
It almost feels like you need to develop like an intuition for what kind of methods are going to be able to be useful in your work. And Victor, we've talked about this before, like looking for almost like low-hanging fruit where humans just like fail or not as good as something where AI can come in and help with that. Which honestly leads me to my next question, which are things we've like talked about before. So you have this emerging area like in space where, for example, Planet takes pictures of the entire Earth like how many times? Like with what frequency? Every 3 days, every day?
No, every day. It's almost daily imagery of all of the Earth's landmass.
Yeah, exactly. And this creates, like you were talking about, huge amounts of data that you have to parse through. Whereas in the space domain, like for example, when I'm looking at my landing site on Mars, I have on the order of like 10 or 20 images to parse through. And so it's almost like completely different paradigm. And to bring into the work Roberto and Victor have done, when you have such a large amount of data set, can you even use AI to like learn things about your problem? Is it possible to like learn physics, or as Roberto, I know you do work to like import physics equations into the AI. So I would just love to get everyone's thoughts on like this topic and like how has an AI like enabled like big data versus small data, and what can you use from that?
Who wants to start?
Yeah, who wants to start? I asked a lot of questions.
I can tell you when this, I don't know if you know this video generation model that OpenAI recently released. It's called Sora. And the day it was released, there was one colleague from the University Rey Juan Carlos in Spain, she's a space engineer, and she works a lot in fluid dynamics. And she saw one example video in the OpenAI blog post, something like 2 pirate ships like navigating in a cup of coffee. It was really beautiful, but the things that the physics of the coffee while the ship was navigating looked so realistic that she asked me, "But Victor, is this learning physics?" And I said, "I don't know." nobody knows. Well, I don't think nobody knows. And actually, the company didn't release the model as a video generation model. They did it as a step towards a world model. Like they claim they can learn how the world works by looking at the world at scale. And that made me think a lot about this conversation that Roberto and me sometimes have about emergence in language, in models, in machine learning versus constraining the model to learn more effectively what you want that it's real.
Well, you already have deep learning models that are doing things like modeling the weather with higher accuracy and higher spatial resolution than some of the best sort of typical models. That would be like a physics model run on a supercomputer at a certain spatial and temporal scale, and you're solving the fluid dynamics equations, and you're calculating the pressure, temperature, et cetera, at every point on your grid, and using this to model the weather and predict a 7-day forecast. But you can take all of that and use it as training data into a deep neural net, and it can run inference much faster than your supercomputer computational fluid dynamics model, and you can model it at different scales, and in some cases the accuracy is so good that we can use that in lieu of the big model.
You're talking about GraphCast.
Yes, I think that's what I'm thinking of.
One of the issue when I would say, persons started putting in the spaceflight mechanic communities papers about, using neural networks for astrodynamic problems, right? The reaction at the time was like, well, you're using all data, that maybe you simulate, right? Because, in space general, there is a scarcity, data, especially, because we don't have, I'm not talking about images, I'm talking about more trajectories and things like that, right? Says, well, but how do you know what is he doing, right? We have the physics here, why do we need this, right? Actually, one of the arguments of the older generation, I would say, of the astrodynamics is like, well, we know the first principles, we know the equations, so why do we need the data? And I remember a colleague of mine, however, pointing out a few years ago that we need to find a way to embed physics into these neural networks, because otherwise, you show a picture, it was interesting. It was I don't know if you know the fable of the
Pied Piper.
The Pied Piper and the mouse, mice going, follow, and it showed this picture of the mice going through a cliff, right? Simply because following, the idea was that you follow machine learning, you don't know what you're learning, right? And you jump off the cliff. Actually, fast forward a few years, it happens. Now we're talking about physics-informed neural networks, where the idea is that the data are constrained by the physics, right? This is extremely important because, again, guidance, control, navigation, spaceflight mechanic people, just need this kind of anchor to the physics, right? So this helps a little bit. Indeed, actually, we're going from a situation where on one side, like with language and knowledge, right, we do have a big data, but little physics, versus on the other side, we have a lot of physics in the sense of equation, but very little data. So physics informed, it's kind of at the balance in between. And for space is extremely important, right, because it ties to the physical, aspects.
It constrains the responses of the neural network.
Constrain the response, and also can help with potential even certification, right? One of the trends that I'm having, for example, when I now train, what they call safe AI, or trusted autonomy, what you do during your learning phase, you always constrain, right, the system, not only to abide by the physics, but also to have some robustness, to put some certificate, to have a Lyapunov, function into the game that you you make sure that you learn a exponentially stable system or exponentially contractive system, whatever. I mean, there's a lot of work here at MIT that with this contraction mapping, contraction system, right? Contractive systems that are important. So I think that we're in the right direction there. It's just a matter of trying to elicit more understanding from both communities of how you can use this technique effectively to enable trusted autonomy, especially for space systems.
Yeah, thank you everybody for those answers. I think the last question that I'll ask, and then maybe if we have time, we'll open up to audience, is where does everybody see the future of this work going? I know some of you are working on some really interesting missions that have upcoming AI use cases, and I'd love to hear where you see the future of AI in space and your work.
That's from me?
Yeah, for everyone.
From that way.
Well, yeah, so a lot of the work that I've done so far isn't actually fielded or used for anything yet. So that it's kind of taking those next steps to deploying it in the real world. So that we start with the research, we prove it out offline, we prove it out in simulation, we show some sort of demonstration, maybe even some flight demonstration to show that it works in theory. But we're still working on making those last, getting to those higher levels of, technological readiness where we can prove that it works on real systems. This is obviously a big challenge for self-driving cars. It's an even bigger challenge for space-based systems. We're starting out with places where machine learning is doing things that can't be done without machine learning. So there's the most reward for the risk that you're taking with using machine learning. Being able to detect on spacecraft anomalies that you didn't expect, like add-ons to the system that are still relatively lightweight, that can just straight up add value without adding risk. That's kind of near term. And then longer term, I do see a lot of those technologies that are totally game-changing on the ground when you have lots of data being slowly brought to the space domain, but maybe a few decades behind.
Yeah, well, I wouldn't bet against the power of scaling up things and end-to-end learning, to be honest. Back in 2019, when I saw the news about GPT-2 back in the day, being able to write paragraphs that are grammatically correct in English without being taught English at all, I was puzzled. And now we take that for granted. We don't test whether language model it's better or not because it writes better English in terms of typos. No, it's just granted. So
That was the bar. Don't make typos. Now the bar is explain this joke to me.
Yeah.
Yeah, exactly. But you take for granted that the English is correct.
That's right.
So in the same way, I think that the same can happen with things like physics and the world models. That right now, we are puzzled seeing that a model can emulate the behavior of the light and the fluids, like basic things. But in 2030, we will not be evaluating that because that will be taken for granted. And I don't know that in the same way that Noam Chomsky is not having his best time now because the formalities that he created for grammar and language are not so popular now. I don't know if that will happen with physics too, Roberto.
Maybe.
But yeah, I wouldn't bet against end-to-end learning at scale.
I can say a little bit about what I'm excited about. So when Planet first started, they were an aerospace company. They built satellites. And once they had a fleet of satellites, then they became a data company. So taking data and selling satellite data. And what the company is working towards now is to become a platform company. And our CEO, Will Marshall, has this vision that he talked about at TED a few years ago of a queryable Earth. Imagine like a type of like Google search engine where you can go and you can ask it, how many trees were cut down last year? And that the system, having observed change as it was happening over the entire world, could tell you how many trees had been cut down or lost to wildfires or any number of measures of human activity or planetary health. That is the kind of platform that Planet is working towards building, and that is something that AI on this global scale will enable. I'm excited about the possibilities that vision language models will open up. They're not quite there yet, where you can upload a geotiff of a particular area and have it explain to you, like a human analyst, what's going on in that part of the world. But I don't think we're that far away from it being able to reason about geospatial imagery.
Me neither.
But that is the future. So these are some of the things I'm excited about.
Yeah. Personally, I'll keep pushing the idea of transferring, all these, deep learnings and beyond ideas into the aerospace domain. I'm just waiting when it's going to be the tipping point when the gates open and the floodgates open and things will come, because there's a lot of pressure. I've seen it building up in my community, that all these successes that you see on these others, yet on the aerospace domain, you don't see them yet, right? Yeah. And I think at a certain point there'll be a tipping point where things, you just have to change the way we do things in a classical way.
There's this new swath of exciting aerospace startups that are trying new things and are willing to make mistakes, experience failure, but they're building some really exciting novel technologies.
The pressure is going to be on the government, the agency, the funds, right, and the ability. That's what's going to happen, right? I think also we're in a situation that politically the world is going, we don't know where it's going. There's a lot of, there might be a crisis, right, that will force us to go in a certain direction where we will just open the floodgates, to AI, and we will just take risk because we have to. I'm not saying that we want a crisis, right, but we might.
Say, are you worried or excited? Couldn't quite tell.
Both. No, I seriously both, because I'm worried and excited on one side because
You're talking about like another Oppenheimer moment or what?
I hope not to the level.
Like climate change, but like
I don't know. I'm just saying that I can see everybody. If you talk with the people in different parts of the governments, everybody's saying, yeah, it's coming. We're gonna head towards some global crisis. Does it mean war? I don't know. It's like, but I can see that, and I've seen on the other side a little bit. People started looking at AI seriously in terms of taking risks that I don't see a civil entity like NASA doing it. All right.
Yeah. Yeah.
And why is it that, right?
Yeah.
Why do I get $5 million from to work on hypersonic, from DoD, and NASA? If I go and tell them Meta Rail, AI is you're crazy. We don't do that, right?
Yeah.
So something is happening there. What I'm trying to say is that either way, hopefully the most benign, way, as I call the floodgates will open, but there's a lot of pressure, on changing things because there's too much success. The interesting thing is that it's driven now by language, which is somehow far away that you can think, the popular conception from physics, right? How comes that this language now you're talking about that
world model?
Yeah. So anyway. So I stop here because I don't have a crystal ball, but
No, but I think he can be right. Like the new startups taking risk can be like the equivalent to small companies like OpenAI like 10 years ago, and like against classic companies like Google that don't take risks. And now, so it might be that's the key. New companies, new startups.
yeah. Well, thank you so much, everybody, for answering these questions. Mark, do you think we have time for like one quick audience question or? All right, if there's any burning question that must be answered by our panelists, I'd love to hear from the audience.
Hi, I'm wondering if you ever ran into a situation where you thought AI would help a problem, but in reality it turned out that the classical, more simple methods actually ended up performing better?
It's a great question. Does anybody want to take that?
A lot of times, yeah.
I say all the time, or equivalent. You're like, oh no, I just learned an approximation of the classical method. Darn.
Like lab.
I've seen situations, but this is a little bit naively at the beginning of people working on solving problems that, like solving the Kepler equation astrodynamics with neural networks. And my question was, why do you do that?
Yes.
You don't need to do that, right?
Yeah.
I guess it was, maybe the excitement. And it was partly coming from, the fact that people wanted to try stuff.
Apply anything to
Apply anything.
Apply to everything.
The one concerning thing, however, is that also that there is a danger, and the danger is what I call the mud in the water, right? That people start applying left and right,
Yeah.
These methodologies that do not work in many cases, and then, distrust. The community start distrusting this.
Yeah.
It's like,
It's
this
easy to
doesn't
trick yourself into thinking it's
Right.
working too, even if it's not like obviously overfitting. Sometimes machine
Yes.
learning will latch on to like features that let it cheat that you don't actually want it to use.
Actually, I have a case that I recently was reading that there was a situation where apparently with X-rays machine, right, they were trying to, they were claiming that they were doing better than doctors, right, because
Yeah.
they train them. It turns out that when they look at this deep dream explanation, it turns out that the system had to learn some tag that was behind the X-ray and was doing the prediction better than the doctor.
That's the
So
shortcut.
it was not looking at the body.
Yeah.
It was looking at some features
Yeah.
that were embedded in
Trick,
some
yeah.
language there. So anyway, it's easy to trick. It's easy to trick yourself, but it's people has to be careful because it might create damages, right? Because people distrust. Say, "Oh, I told you. Why would you use that? This is."
To me, I've been working a lot in time series forecasting, and that field right now it's dominated by deep learning and so on. But it took a lot of time. Like 2 years ago or 3 years ago, you still saw in Kaggle competitions like forecasting challenges with classic statistical models being top one, like ARIMA-based models performing much better than neural networks. So yeah, many times. Yeah.
It's really interesting. Well, I think that's all the time we have for today, but I encourage anyone, if you'd like to speak with our panelists and hear more about their work and like who they're representing, I would really encourage you to follow up with them. But with that, let's please give a round of a hand to everyone who's presented today.
Thank you, Adriana.
Thanks.
Thank you.
Yeah.
All right, thank you so much. We now are breaking for lunch, so enjoy the delicious food, and we will reconvene at 1 o'clock.